kids. Hey! This is the final installment of Basic Circuit Stuff. This one is going to be talking about energy and power. Yes, you probably heard about power when we talk about circuits, and that's what this one is going to be about. Okay, so we're going to talk about power. So this is energy. We're going to talk about energy and power. But first, remember, power is defined as the rate work is done. Okay? And if you remember, okay, work is when you change energy. So in this case, when we're talking about electrical, power, and we're talking about work done on charges, you should be thinking, oh, well, what energy am I changing? Well, I'm changing UE. So hopefully we remember this equation from our formula sheet, which is Q times delta V. I'm going to put a little rectangle around that because that's on your formula sheet. So again, make sure you can find it, locate it, and everything else. Okay? But let's say I have a circuit like this where I have two batteries, and for some reason the batteries are working against one another. And this actually happens in a car, and this is how you can recharge a car. So I have these two batteries here, and I have a resistor. I'll call this resistor 1, resistor 2, resistor 3. Just for the sake of this, I'm going to call this battery 1 and battery 2. Sometimes you will see this little epsilon to represent, it's called electromotive force. Electromotive force is just another fancy way of saying voltage, but just so that I'm going to be calling this V and this something different, so we can see that this is from the battery and that's for the resistor, okay? All right, but let's pretend I have a charge. And remember, because we're talking about current is positive charge, so let's pretend that we're a little positive charge right here, and we're going to work our way around the circuit. And we're going to talk about what happens to our charge's energy. Okay? So if we're talking about our charge's energy as it goes around the circuit, so well, first it's going to encounter this battery. Well, is that going to add energy or take energy away from that charge? Well, it's going to add energy to my charge. How much energy is it going to add? Well, it's going to add Q, it would add Q times V. So again, I'm using this equation, okay? But for this, it would be Q, whatever the charge is, times V. So far, so good. Then my little charge, hey, I have more energy because, my battery gave me more energy. Woohoo! And then I get to my resistor. Now, the resistor is going to use some of the charge's energy. So then that would be a minus, okay? So it would be minus Q times V1 for whatever that voltage is. Remember, V1 would be equal to I1 times R1 because we have our very nice equation. Okay, so we got to this. Hey, I gave a little bit away. Uh-oh, shoot, I get to this one. Do you see how this battery's facing the wrong way? Well, if I want to go through this, I have to give more of my energy away. How much? Well, then I would give minus Q times this. Okay, and then I get to this one. Oh, shoot, I got to give more away. Q times V2. And then I get to this one. Minus Q times V3. And, okay, because I'm back where I started, and I, have to follow the law of conservation of energy, if I gain energy and then I gave it all back, my change in energy would have to be 0. Does everybody follow that? Okay. Okay. Well, hopefully that makes sense. That would be in terms of energy, so I'm gaining and losing. But I just want to show you, so that's the energy piece of it. And remember, guys, do you remember what a volt really is? It's a joule per coulomb. So if I go a volt times a coulomb, I get joules, which is energy. Hopefully we're good with that. But if I do, and I divide by time, 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 oh, it's still 0. If you take a look, now I have energy per time. Oh, that's the rate my energy is changing. That's the rate I'm doing work. Oh, that's power. So I would get power equals And in this case, you would get plus, hey, Q over T, what is that? Oh, that's current. This is also current. This is current. This is current. And this is also current. For this particular problem, because how many junctions do we have? Oh yeah, none. So that all of those currents have to be the same. But this is going to tell us our equation for power. Our equation for power is going to be P for power equals I for current times V. Okay? Which, now remember, this is measured in, okay, this is measured, I is measured in amps. Okay, so it's really amps times volts. An amp is really a coulomb per second. A volt is really a joule per coulomb, which means I end up with a joule per second. A joule per second is power. A joule per second also has another name. Does anybody remember what it is? Oh, yeah, that's right. Power, a joule per second, is the same thing as a watt. What? A watt. Okay. So that's power. The nice thing with power, as you can see, no matter what circuit you have, power always adds up. Which makes sense because if you add more stuff in your circuit, it's going to eat up more power. Okay. There you go. Hopefully that makes sense. Bye, kids.